We call complex number. Complex number is a number of the form complex number. In this book they use the letter Z. I like to put little slashes through my Z so they don't get confused with 2's. Z equals A plus BI. Oh, that's horrible. A plus BI as the general form of a complex number. Okay? And a complex number has two parts, as if you probably remember that this is the real part and this is the complex part. And if it's just like, even all real numbers are also complex numbers, like 5 is a complex number. So, but that's just like 5, you don't have to write this down, but that's like 5 plus 0i, right? Would be a complex number as well. And a pure imaginary number, like Z equals 3i, that just doesn't have a real part. So over A is the real part, and B is the BI is the imaginary part. Okay, but there are very useful branches of math that use complex, even though they're imaginary numbers for the most part. Complex numbers, you can do calculations on them, and I saw a story a couple years ago that everyone said, well, what do you need to know all these imaginary numbers for and stuff? Well, they're using lots of higher order calculations of mathematics and stuff, but apparently they use them all the time for like for aerodynamics and stuff, like modeling airflows and stuff over wings and cars and all that kind of stuff. But that was just one of the places. But imaginary numbers, even though they're imaginary, they're used for real applications to solve real life problems. Okay, so we're going to be graphing imaginary numbers in the complex plane. So this is a complex plane, and instead of this being x and this being y, this is called the real axis over here, real axis, and this is called the imaginary axis over here. Okay, imaginary axis, and this is all in your book, but kind of regurgitating that information. But so if you want to graph a number like -3 plus 2i in the complex plane, this is just like x and this is just like y. So you would go backwards 3, 1, 2, 3, and then you would go up. This is like the I-axis, and then you would go up 2. Okay? So this would be the point on that axis, -3 plus 2i. So that's how you graph numbers in the complex plane. If you just wanted to graph -3, that would just be this point right here. There's no I part. If I just wanted to graph, say, -4i, where would that be?
It would be 4 up on the imaginary axis.
4 down, right? 4 down. 1, 2, 3, 4. So this would be the point -4i, and so forth. So that's how you graph points in the complex axis. Okay? Absolute value of the complex number in a second. So this thing here, the distance, well, maybe I should just move on. This absolute value, absolute value of a complex number is the distance between 0, 0 and AB. where A and B are the coefficients of the real and the imaginary part, respectively. So Z, if Z is a complex number, it's in this form, A plus BI. Okay? So the absolute value of the complex number is the distance between 0, 0 and AB, and that can be written as like this: A plus BI, which is equal to R, which is called the modulus of the complex number, which is equal to the square root of A squared plus B squared. So it's really what we've been doing. It's just taking a vector, really, and putting it into a complex form, and it kind of works the exact same, calling these things. So instead of I being the x component, I is now the vertical component, and A is the horizontal component. Okay? So, for instance, you might, if I wanted to find the absolute value, of -3 plus 2i, I would just take the square root of -3 squared plus 2 squared, which would give you the square root of 2. It's just the distance from the origin to that point. So it's just like the radius, and that's why we call it r. Okay? Trig form of complex number. What else do I have? So if I wanted to graph that real quickly, that graph. So -3, we already did that one, plus 2i up here. Okay? Here's that point. This is r right there, modulus. Just the distance from 0, 0 to that point. What's wrong? Questions? Nothing. Okay. Then we have trig form of a complex number. Let's change colors. Trig form of a complex number, and this is just kind of, it's easy. Complex number. If you have some complex number out here in space, let's put an arrow on the end of this one. Some complex number, let's make it pink. Why not? Going over this way. Okay? This angle here is theta, the angle between the x-axis, just like it was when we're defining a vector in trigonometric form. Okay? And this is r. Okay? So just like with a vector, very similarly to that, z can be written in complex form as r times the cosine of theta plus I sine of theta. Okay? So r cosine theta gives you basically the horizontal component, and r times sine theta gives you the vertical component, where this is the I-axis. So, questions? Easy? Okay? So, and again, this thing is called the modulus r, which is the length or the absolute value or the magnitude, if you will. Okay? And theta is called the argument. Okay? It's the argument. Don't argue with me. It's just what it's called. Okay. Got it? Easy so far? So now we're going to do an example. Example! for example, write 2 minus 2 root of 3I in trigonometric form. In trig form. Okay. So the first thing you want to do is find R. How would I find R?
Square root 2 squared minus 2 squared.
Yeah, you got it? So you got to be a little careful. It's 2 squared minus, or plus, sorry, negative 2 root of 3 squared. Alright? Which, if I do that, I get 4 plus 4 times 3, right? You guys see where I got 12 from? 2 negative 2 squared, root of 3 squared is 3, so 4 times 3 is 12. 4 plus 12 is 16, so this comes out to be what? 4, right? Huh?
I'll just keep going.
Yeah, it comes out. Yeah, whenever you square something, comes out. Okay. Now we also know that cosine of, just like it was for vectors, cosine of theta in this case is equal to b over a. Okay, just like it was y over x for complex numbers. So it's just the y part over the x part. And so cosine theta in this case is equal to negative 2 root of 3 over, oops, not cosine of theta, I'm sorry. Tangent of theta. Sorry. Tangent of theta, that's what happens when they don't want to. Tangent of theta is equal to b over a, which in this case is negative 2 root 3 over 2, which is just negative square root of 3. And then you have to figure out what your angle is. Well, looking at the picture, 2 minus 2 root of 3, so if I go over 2 and down 2 root of 3, which quadrant am I going to be in? Fourth quadrant, okay? And so when I take to find what theta actually is, even though the tangent of theta is equal to this, I still have to pay attention to which quadrant I'm in. And I'm going to go that, I'm going to take the inverse tangent. If you don't remember your unit circle, this is a point, whoops, this is a point on the unit circle. Anyone remember what that is? When is inverse tangent, when is tangent equal to negative square root of 3? It's either 30 or 60. It's 60 degrees, okay? So this, if I do inverse tangent, it's negative 60, okay? But that's not the angle. You want the angle from the x-axis to that angle. So what would that angle be? So that means that theta is equal to 360 minus, that's about minus 60, which is 300 degrees. Okay, so now I have my r, I have my theta, and I could write this as z equals 4 times cosine 300 degrees plus I sine of 300 degrees. And you could either write that in radians or in, if they don't specify, either in radians or in degrees, but if they, doesn't matter. Okay? Questions on that? No? Okay. It's not always, well, it's pretty easy, but what if I wanted to write, negative 4i in trig form? You don't have to go through all that. Just think of where it is, okay? Graph it. What I would do is select the arrows on both ends. Because it's very useful to have a picture of what point you're talking about. Where is negative 4i? Yeah, straight down 4, right? So I'm going to go straight down 4. 1, 2, 3, 4, and put a point there. So here's negative 4i. What angle do I need to turn through to get to here? 270 degrees. So that's my theta, right? And if you did try to use inverse tangent of negative 4 over 0 is going to give you an error, right? So you can't really do that, so you have to look at the picture in this case. What's the length of the modulus? How far is it from here to here? Just 4, positive 4, because the angle will take care of the negative sign. See? Right, so that's just 4. Okay? So you'd write it as 4 times the cosine of 270 plus I sine 270. Got that? So you don't have to worry in that case, or 3 pi over 2 if you want that. And that's it. Yes? Easy? Okay, so a lot of times you want to draw a picture rather than go through, doing the finding the angle and all that kind of stuff. Then they go forwards. Okay? So what if I did convert, whoops, wrong kind of paper. Right, we're almost done. Well, not quite. Right, let's do this one. I'm changing my square root of 6, cosine of 5 pi over 6, plus I. You put the I first, so you don't think that the I is underneath the square root sign. So I sine of 5 pi over 6, 5 pi over 6, in A plus BI form, meaning standard form. Okay? They call this sometimes in A plus BI form, or sometimes they call that standard form. I think in the book they call that standard form. So all you have to do is multiply things out. All right? So you leave root of 6 as root of 6. You guys remember what the cosine of 5 pi over 6 is?
Negative 3 root 2.
Very good, Zachy. Okay? That's negative square root of 3 over 2. Okay? Plus I, and remember what the sine of 5 pi over 6 is? Positive 1/2. You guys are good. 1/2. And then you just multiply through and simplify. When I multiply square root, you can multiply square roots together. You just can't add them or subtract them. So this is negative square root of 18 over 2 plus root of 6 over 2. I guess you could simplify that a little bit. Square root of 18 can be written as 3 root 2, so you can't do much with it. Just change it into negative. If you left it like this, I'd be okay. So negative 3 root of 2 over 2. Whoops, I forgot the I. Don't forget your I. Plus I, and this you just have to kind of leave as root of 6 over 2. Questions? Easy? Easy as pie? Okay. I'm going to give you one more thing. That's all you really have to know for tonight's homework. Okay? I'm going to give you one more thing that it won't be until tomorrow's night's homework, but I just want to give you the formula so I don't have to teach it tomorrow, because the second thing that I have to teach you about is the Moab's theorem and finding complex roots and stuff, and that can get a little confusing. So I just want to teach it to you. It's just 2 formulas, and then but you won't have homework on the second part. Okay? So the next thing is they just derive these formulas, multiplying and dividing complex numbers. Okay. And so there's a formula that they derive, and the way they derive that is just actually foiling out these complex numbers. But say you have 2 complex numbers, z1 times, so this means times, it's not dot product, okay? Maybe I should write it like this. Z1 times, let me try again. I don't want you to get confused with the dot product. So z1 times z2 is just equal to r1 times R2 times the, oh, I should have written this, times the cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. And theta 1 and theta 2 are just the thetas for each of those respective complex numbers, okay? And very similarly, Z1 divided by C2 is equal to R1 over R2 times the cosine of theta 1 minus theta 2, like this. Whoops, I should add another parentheses here. Plus, that works. Whoops, no, I don't want to end that parentheses there. I want to end that parentheses there, right? So it's R1 times R2 plus I cosine of theta 1 minus theta 2. In other words, take the two vectors, multiply their moduli, ooh, that's a good word, moduli, and then add together their angles, okay? So for example, say you have Z1 equals, Z1 equals 8 cosine 120 plus I sine 120. And Z2 equals 6 cosine 150 plus I sine 150. Okay. If I do that, so if I wanted, whoops, Z2, sorry, Z2 equals it. So Z1 times Z2 is equal to 8 times 6, which is 48. And then you add together these two angles. So it's 48 times the cosine of 270 plus I sine of 270. And then if they say leave it in trigonometric form, you'll leave it like that. But if you want it like in I plus A plus BI form, then you would actually multiply this through. Cosine of 270, who knows what that is? Zero. Okay? And sine of 270, you were right on that one, which is -1. Okay? So that's -1. So all I would get, -1i, right? -1i. So this would just be the same as -48i. Okay? So in other words, if I take what exactly that means, and if I have this complex number, which has a modulus of 8, and it's over here somewhere like that, okay? And this complex number, which has a modulus of 6, and somewhere over here, and I multiply those two complex numbers together, I get a complex number that's down here with a modulus of 48. And you would, like when you're doing mathematical calculations on some things, a lot of times you would want to multiply complex numbers together. Maybe you're finding airflows on wings or designing the most aerodynamic car or something like that. Okay. And then furthermore, if you want to divide them, you just plug and chug. It's just easy. Just plug into the formulas. So this just becomes 8 divided by 6. 8 divided by 6 times the cosine of 120 minus 150. So that's cosine of -30 degrees. So you subtract, this is theta 1, and this is theta 2 over here. Okay? And so you subtract, so cosine of negative 30 plus I sine of negative 30. And this one doesn't come out to be a nice, neat, even one like that. This comes out to be 4/3. Cosine of negative 30, I think, is positive root of 3 over 2. Yes? Positive root of 3 over 2. And I sine of 30, I sine of negative 30 is negative 1/2. Good. Okay? Negative 1/2. And I just go through that for, so this, and then if I wanted to simplify that, that becomes 4 root of 3 over 6, right? 4 root of 3 over 6. Whoops, I forgot my I part. Don't forget your i's. Okay? Did I do that right? 4 root of 3 over 6.
To simplify that, 2
And,
root of 3 over.
Oh, thanks. Hold on a second. Don't get me confused. Minus I times 4 over 6. And Zachy said I could simplify that, which is true, which is 2 root of 3 over 3 minus I, or 2/3 I would just call it, minus 2 over 3 I. Okay? Easy enough? Easy stuff, right? Okay, I'm done. So your homework, it's on my website, but I'll write it down. It is page 452. 1, 4, 5, 6. 1, 4, 5, 6, 8 through 22 evens. 24 through 46. Every other even. And then 47 through 61 on. You could blame Mr. Beamer for picking all these problems. So I let him pick the problems. Sometimes I make up. But there it is. Okay? So you can start.